All right, so there's a pump curve from page 152. Let's have a look at this one and see what we got. All right, we got a few things. First thing we've got 4 different impellers that can be put in this pump. So we've got 4 different pump curves on one graph, because this is a model, 10LC, and you can put different impellers in it. So for each impeller, they give you a curve. They're kind of hard to read, so I wrote them by hand up there: 7 3/4, 7 1/2, 7 3/8, and 6 7/8, right there. And then those pump curves run down through the graph. Then the efficiency curves kind of run through there. They also have brake horsepower lines down here. Those are read over here to the right. Okay, what else do we got? We've got number of bowls. Okay, so this could be a multi-stage pump. You can put more than one impeller, more than one volute on this thing, up to 3. And then you adjust the efficiency as shown, depending on how many bowls you've got. You know, they give you the information on the impeller. Usually they give you the RPM. Yeah, 1460 there, I think. Okay, so that's some of the information on that pump curve. The basics are there. You got gallons per minute across the x-axis and total head and feet across the y-axis, but then you've also got some horsepower stuff over here on the other y-axis. Okay? So that's how this thing's set up. Okay. So one of the main things you see with this is each impeller has its own line on the pump curve, plus the efficiency is affected by the number of volutes on this thing. All right, there's another one there that has actually 5 different impellers that could be used. A lot lower efficiencies on this thing. I believe it's an open impeller. Okay, this is by Hydronics. Again, you got gallons per minute and total head and feet over there. So that, you know, all pump curves seem to have that for X and Y. Then you've got 1, 2, 3, 4, 5 different impellers that can be put in that. This thing has another little addition, that it has the NPSH total suction lift curve on it as well, and it has efficiency curves. Okay, 1750 RPM for that one. All right, so the NPSH there shows the required NPSH for the pump to work properly, okay? So that's what you get if you read the NPSH. Alternatively, you can also read the lift, the maximum lift you can have with the pump for different flow rates. Okay. So these multi-stage pumps, you have more than one stage, they call it a bowl, it's a volute. You have to factor the TDH and the horsepower up by the number of bowls too, though, so remember that. The pump curves are basically made for one impeller or one volute. So if you're using 2, you have to double the horsepower and the TDH to account for that. So we got a few little problems there on page 151. Let's just go through those and see if we can read these things. All right, it looks like we've got kind of different ones than you do. We'll use the ones I've got here. So let's go with a TDH, brake horsepower and efficiency for a single stage pump with a flow of 300 gallons per minute. We'll use the 7 3/8 inch impeller. Okay, a little different than what you got in your book there, but same sort of idea. So we got 300 gallons per minute. Locate that. And then just read it up until you intersect the information that you need to know. So what do we got for TDH? I got about 27 and a half. I don't know. Is that about right? Okay. How many PSI would this thing develop then? You know, if you're reading a gauge on it, what would the PSI reading be for it? Yeah, 0.433, yeah. Yeah, okay. So I read about 11 or 12 PSI. Yeah. Okay. Now there's four curves. We're on the second one up from the bottom. So when you do the brake horsepower, read the second curve up from the bottom. There's 4 brake horsepower curves. So read the second one up from the bottom. And you know, that's it's not easy to read in there. Yeah, it's 2.5. Okay. Yeah, I don't know. I was going to say 2.5 or so, but we could check that, you know. And then what's our efficiency in there? Or is it between 80 and 81? Or okay, yeah. I mean, what is it? It's hard. I'm having a hard time reading. Inside the bubble. Is it? Okay. Yeah, I'd say it's inside the bubble. So yeah, you're right. 80, 81. Okay, we'll call it 80. Okay. So we got any questions on that? Are we doing all right? Now, a couple of things here. You got to subtract 4 off of that, okay? So it's 76%. That's this little note over here. So depending on the number, what they call bowls, which are actually volutes, you know, that you've got to subtract off the efficiency. And then the brake horsepower is about 2.5. Okay. Now, why don't we check this real quick? Let's find the water horsepower. Okay, so that's 27.5 feet, 300 gallons per minute, divided by 3960. So 27.5 times 300, divide by 3960. Yikes. 0.12. No, I didn't multiply properly. 27.5. There we go. Times 300. Divide 3960. So I got 2.08. Then our efficiency is 76%. So to get the brake horsepower, we'd take the water horsepower, the 2.08, and divide it by 0.76. 2.7. Okay. So the brake horsepower is what you need to come out of the motor for this thing. Okay. You okay with that? Okay. So that's how you could read one of those, okay? Just watch, understand there's more than one impeller line on there, so just be sure you're getting to the right line for the proper impeller. Make the adjustment there on the efficiency too. Okay. All right. Now, what if we use a double stage pump and a flow of 300 gallons per minute? What would happen then? Okay. Because you're kind of getting the same numbers, right? But now you got a double stage pump. So what's going to happen to that 27.5 TDH? It doubles, yeah, because you got two bowls now. It's taking that 300 gallons per minute and running it through two volutes, so it's doubling up the head. So that'll be 55 feet. But again, there's no such thing as a free lunch here, so that's going to double up the horsepower you're consuming too. Okay. So that'll be 2.74 times 2, which is 5.5 or 5.48. Okay. And then how about the efficiency? We read 80 off the chart, but how do we adjust it this time? Yeah, just -2 this time, so a little bit more efficient. Okay. So that's one little thing there. That's how you adjust for if you've got more than one bowl, as they say. So just be aware of that. You often, if you got a multi-stage pumps, you have to adjust how you read the curves, the head and the horsepower. Okay. Okay, let's have a look at this one. This is from the Hydronics. This is a self-priming pump. This is an open impeller pump. I think it's meant to be set up above whatever it's pumping. So let's find this stuff for a double stage pump with a flow of 350 gallons per minute. And I guess we need to pick an impeller off of here. Let's see. All right, why don't we just go with the 8.5. And let's just go single on this. Let's change this to just single. All right. So what do we got for TDH? Is that? Yeah, something like that. Okay, how about the efficiency? Yeah, about 60. All right, now the horsepower, notice they don't give it to you here directly, but what they have are motors that you should use. So what motor should you use for this situation?
Go for 10.
Yeah, go up. So it'd be a 10 horsepower. I mean, if we want to, it's easy enough to run the numbers if you want to know. So water horsepower would be 57.5 feet. What, 350 gallons per minute? Over 3960. So you could run that. I'm sorry?
Where does it show you to do the 10 horsepower?
They've got curves, they're dash curves that they're labeled in the lower right there. And
I see them.
okay, so mhm. So 57.5 times 350 and divide by 3960. So I'm just getting a little bit over 5 water horsepower. But then we got to take that and divide it by the efficiency, which is 80%. So divide it by 0.8.
No, you said 60.
Oh, 60, thank you. Yeah, there we go. So 5.08 divided by 0.6. Yeah. So 8.5. Okay. So that's why you need the 10 horse motor. Okay. Motors don't come in, every possible horsepower rating. They kind of jump. Not quite sure the lower ones, but 1, 2, probably 2.5, 3. I don't know about 4, but there's 5, 7.5 I've seen, and 10. All right. Now they also have this NPSH stuff that you want to have a look at. So for this pump, they're telling you, that if you calculate the NPSH like we did, you better have at least 10. And what they're saying is you shouldn't lift the water more than 20 feet. That's the maximum lift for this pump. And if you actually have it installed and you're running numbers on the NPSH, it should not be less than 10. If it is, this pump won't operate properly. You got any questions on that? All right. Yeah.
So if we need 8.5 brake horsepower to move 350 gallons per minute, and it's have a 10 horsepower motor, is it going to try to move more water?
It'll run on the curve is what it'll do. So this pump will just call for 8.5 horse. So I think that's I mean, it's just calling for 8.5 horse is all it's doing. I'm not familiar enough with motors. What, okay, so you,
Because I thought we were talking on Wednesday that it's gonna try to move as much as it can.
it's running on the curve though. That's what this particular pump does. So if it's here with this impeller, all it's gonna ask, it's gonna call for 8.5 horse. So I think the rating on the motor is the maximum horsepower output. It's not what it just puts out.
And then your impeller kind of regulates
Yeah, the
what the
speed of the
horsepower,
impeller and the setup on the
the
balloon.
size,
Yeah, I
and,
was gonna
yeah,
say regulate, that's a good word for that. I'm just starting to think through motors, so I mean, motors, they have windings on them, they have a certain frequency coming into them, you know. But, yeah, I'm pretty good on this, that, you know, that this pump runs here, and I know that. And when it runs there for that particular flow, it's, yeah, based on the setup of the pump, it's only gonna ask for basically 8.5 horse. So that's what the motor will deliver. So I'm not sure what physical property about the motor changes to deliver the horsepower.
Yeah,
It's the torque, I mean.
Yeah.
But when you start getting into the windings and stuff on the motor and how that, you know, I'm not about that. But, you know, as far as how the motor changes to deliver what the pump needs.
does the motor change at all, or is it just the impeller that brings 8.5 horse out of it? The
Well, it's,
pump
yeah,
and the
it's
impeller.
the shape, you're right, it's the speed of the impeller and the kind of that outer diameter that the impeller
distance
spins around,
between-
yeah. Yeah, but it's also, you know, the setup on the balloon, you know, the characteristics of the pump. Yeah,
50.
yeah, so,
So if you have a more powerful motor, it doesn't matter, because it's still gonna only run 750 amps, so it won't change the flow. You understand? It just means the motor doesn't have room for the whole network.
So it'll change the efficiency. Because-
of the motor perhaps, I gotta check on that,
It just feels like if we
yeah.
only need 8.5 horsepower move,
Right.
350 gallons per minute, and we got a 10 horsepower motor, it seems like something else has got to balance.
Right.
Yeah, I'm not sure what's
Maybe
balancing.
it's gearing.
Nor am I, it's nothing fancy, it's not hearing or anything, I don't. I'll ask somebody I can ask. I'll just tell you before the test.
Okay.
Yeah, cause I'm kinda curious too, because, you know, there has to be something about the motor on the output that's changing.
Yeah.
And motors are run by the windings of the wire and the frequency of the current that comes in. And, wait, it's the voltage and the amperage though, right? Anybody do electricity? You guys have been
Yeah.
technical?
Yeah.
Next, yeah, okay, I bet it's the amperage that's what varies,
They're
right?
calling to see.
Yeah,
So it's going to be using less power.
yeah, right, which could affect the efficiency. Yeah. And that has to do with the resistance and all, yeah, I don't know. All right, are we good? I'll look into that one a little bit. I'm pretty sure it's the amperage that'll change. Because that's, you know, that's what, that's what changes in like a residential system when you go through the wires, depending on what you've got turned on. All right. Okay, one other thing here is cavitation, okay? That's something you definitely want to avoid. Cavitation is caused, the true definition of cavitation is you have what are called implosions in the volute, okay? Implosions are when you've got water vapor that forms, and then when it moves to the high pressure area, when it starts moving to the piping, these water vapor bubbles will collapse and they'll implode, and they're kind of like explosions, but they're happening kind of inward, so they're called implosions. And this can chip and destroy an impeller, okay? See if our friends on YouTube have anything. All right, let's have a look and see what these experts can tell us.
Those of us that are familiar with self-priming centrifugal pumps, we know that we must first fill the volute with water. We can now start the pump and watch what actually occurs inside of the pump during priming. After we fill the volute casing with water and we energize the pump, the impeller turns in a counterclockwise rotation. The initial prime of the pump is slung through the volute scroll, or the ever-increasing water channel, into a pressure cavity or a discharge chamber inside the volute. Inside this discharge chamber, the air and water separate. The heavy water falls back down through a recirculation port, and the air then is evacuated through an open-ended line or through an air release device. All the while that we recirculate the water inside the casing and remove the air from the top, we create a low pressure at the eye of this impeller. Due to differential in pressure, atmospheric pressure that we live around every day is higher than the lower pressure created at the eye of this impeller. Due to that differential in pressure, atmospheric pressure outside begins to force liquid up the suction pipe. As liquid moves up the suction pipe, it pushes all the air ahead of it into the volute casing, where it is handled through the recirculation process. Again, the air is handled off the top, and the heavy water recirculates back down into the volute scroll area. I'll close this valve right now and create a suction line capable of pulling a vacuum. Ahead of it moves the air, pushes it into, handles it through the recirculation process, and once the water arrives, the pump then...
That was, I don't know. Okay, let's try another one here. Cavitation in a water pump and valve. Excellent visualization.
Hey, did you know the Capital One Venture Card lets you use your miles for any flight on any...
I didn't know that. Yeah, I guess I didn't know. All right, we'll go with the excellent. Oh, there's a demo there. All right. Now let's see. Brought to you by Mountain States Engineering and Controls. There we go.
Here we have a pump trainer. We have an electric motor with a horsepower meter through a magnetic coupling to a centrifugal pump. The pump itself is made of acrylic, so we can see the spinning impeller inside. We can also see the fluid go through. It's got a gate valve here on the discharge. It's got another valve over here on the suction. And all the piping here is clear, so we can watch the flow of fluid. Right now it's all clear water, so we can't see much in that regard. It's got a rotometer here showing us the amount of flow. But what I'm going to demonstrate here is cavitation. We're going to purposely cause cavitation to occur in the system. We're going to do so by keeping the discharge valve wide open like it is and pinching off the suction valve. What that will do is reduce the pressure in this line, and you'll see this compound gauge show a stronger and stronger vacuum as we begin to pinch off this valve. Now I'll start to turn this clockwise, and you'll see the gauge's indication go down. You'll also begin to hear cavitation take effect. We'll be able to see the bubbles form inside of here as it cavitates after it flashes in the vapor and cavitates into liquid again here. So here we go, closing the valve. And watching the gauge. The gauge will go down. Minus 10 inches of mercury. Minus 12. Minus 14. You can start to hear flashing occur there. 16. More noise. Minus 18. Minus 20. You start to hear that sound that sounds almost like rocks going through the pipe. There's no debris, there's no solid material through here. That solid sounding sound is really the collapsing of the vapor bubbles as they go back into liquid form. You can really hear it now. You can see it occur inside of here. It's a very pronounced action and noise. As the water goes through the valve, it reduces pressure going to the restricted valve. Its pressure drops below the vapor point of the water at this temperature. It flashes into steam, and then after it comes out of the valve and expands again, the pressure goes up And what happens is those vapor bubbles collapse back into liquid. And that's where you get the cavitation effect.
Okay, so there's cavitation.
You can see it happening here. You can also see some bubbles here in the scroll casing of the pump. Cavitation is very destructive, especially upon the metal surfaces. The acrylic surfaces here seem to handle it a little bit better, but with metal surfaces, there's no give. That's very destructive. The metal will become pitted by the high pressure jets formed by the collapsing bubbles. So I just want to illustrate what cavitation looks like in an acrylic tube and what it sounds like.
Very bad thing.
It sounds like rocks, literally like rocks going through the pipe. And again, we cause it by dropping too low of a pressure.
In this video, I will describe some of the causes and effects of cavitation failure. These pictures show examples of the type of damage that is caused by
It
cavitation.
can actually shatter your...
This is a
it can
picture
chip
of a
your
large
pellet.
Kaplan-style turbine runner that is
and the
now
inside of the
removed from
volute.
service at a hydroelectric power generation facility. On the low-pressure side of the turbine blade, in approximately this location, we can see some evidence of the type of surface pitting that is typical of cavitation damage. Another example of cavitation is located in approximately this area of the blade tip of the turbine runner. This next example is also of a hydroelectric facility. This particular facility dates back to the early 1900s and is now abandoned. This is a picture of a horizontal turbine housing. If we look inside the housing about here, we can see the results of cavitation and erosion that occurred over the years of service. Also, notice that if you look closely, you may be able to see what appears to be the results of a brazing process repair in a couple of locations that occurred sometime in the past. In order to understand how a moving fluid can cause the type of damage that we have seen in these examples, it is helpful to review a few basics of fluid dynamics. This graph is known as a vapor pressure graph.
Primarily it affects the impeller itself. It can also affect the interior of the volute. It can really tear things up pretty badly. All right. All right, so the main things that can cause cavitation, if you have air leaks through the intake piping, too high a discharge head, or too low of an NPSH, that's what can cause cavitation. So this is just something to be aware of. This is on page 154. So if you got air leaks into the pipe, that can get you actually air pockets that can form, and you know that those can cause a lot of trouble when they go through in a volute. Now, a couple of things you want to avoid if you've got piping. You don't ever want to have your piping go like that, because the dissolved air in the water will start to collect up there in a bubble, and eventually that can kind of run through the pump. That's trouble. The other thing is if you have reducers, if you need to go from a big pipe to a smaller pipe as you're coming up through your piping, you don't use regular reducers. You use what are called eccentric reducers. You want to hold a straight line on the top. So what you would want to do then would be to have the pipe reduce up towards the top in a fashion like that, okay? Those are called eccentric reducers, as opposed to something like that. You don't want that, okay? Of course, you want to check for leaks on your piping too. Too high a discharge head means you got too much pressure where the water leaves the volute and goes into the piping system. You just have to decrease that. Maybe easier said than done, but you might need to put a second pump in somewhere or something like that. Okay, NPSH is what you're looking at on that video. The energy in that water going into the pump fell too low. The vapor pressure of the water exceeded the NPSH, so it just vaporized. It turned into steam, not hot steam, but you know, cool kind of water vapor basically. And then those water vapor bubbles get into the volute and cause problems there. So what you want to do is reduce the head to increase the NPSH. Okay, so pull the pump down if you can, so it's not too high above the inlet reservoir, and then watch out for fittings and rough pipe on the inlet side. It's a common mistake to put too many valves on the inlet side. You want to put as many of the valves as you can on the outlet side, because that way it doesn't affect the NPSH. So you want to reduce the lift of the water into the pump, and you also want to reduce the head loss of the water going into the pump. Okay. So just a little bit there about cavitation. Let's see. You doing all right with that? Any questions on this test coming up?
Do we have any of those pump problems that we just went over?
The pump curve?
Yeah, is there gonna be?
Yeah, there might be something on a pump curve on there. So with the pump curves, so yeah, there could well be pump curve problems. The thing on these little bit fancier curves, the things to remember, I kind of listed there. So be aware that if you've got a multi-stage pump, you have to adjust both the horsepower and the TDH, okay? Okay, so multi-stage pumps, you have to adjust both the horsepower readings and the head, okay? Just multiply them by the number of bowls you've got when you read them off the curve. Okay, the number of bowls can also affect the efficiency of the pump. Remember that there could very well be more than one impeller on a pump curve, as you're seeing here, so just be sure you're reading the proper curve when you do the reading. And then there was this NPSH curve on this one right here. So this curve you just read over to the right to find what the required NPSH was. So on these fancier pump curves, those are the things you want to be looking for. They're listed on page 151. Other questions on that? Okay. I'll be around during the week, if you got questions, come on by. All right. Call it good?
Thank you.
Yep.